Number 32, chapter 10. We have this helium gas. So I have a picture of a balloon here, and they tell us the density of the helium gas at 0 degrees Celsius is 0.179 kilogram per cubic meter. And density for gases, it's very dependent on temperatures, because if the temperature of the gas changes, imagine the temperature of this balloon rises, what's going to happen to the volume of the balloon? It's going to expand, which will change the volume, and if the volume of the balloon changes, the density of the balloon will change. So one thing to realize is that the mass is not going to change, but the density can. So the textbook uses this symbol rho for density. I don't like that symbol. Let's just use D. So we'll change this to D. So the definition for density. Density is mass per volume. Density is mass per volume. So we have two conditions here. We have condition 1, condition number 1, condition number 2. So the first condition, we have, we'll call it T1. The temperature is 0 degrees Celsius, but whenever you're doing gas law problems, that has to be Kelvin. So that's 273 Kelvin. And V1, notice that no volume is given. No specific volume is given, but I think the easiest way to do it is let's just assume that the initial volume is 1 cubic meter. So that's a real nice volume to assume, because they tell us that the density of the gas for condition 1, D1, is 0.179 kilograms per cubic meter. So what's the mass of the helium going to be if the volume's 1 cubic meter? It's going to be 0.179 kilograms. And that is going to stay constant, right? So if you look at this balloon, let's just say this is our sample of helium right here. The helium inside this balloon has a mass of 0.179 kilograms, and the corresponding volume is 1 cubic meter. Okay? Now, condition 2, what happens here is the balloon gets heated up to a temperature of 100 degrees Celsius. So look, is that change going to affect the mass? No, the mass of the helium is going to stay constant. Will that change of temperature affect the volume? Yeah. The balloon's going to get bigger, so we're going to have to calculate, well, what is V2? We got to figure that out. And then we can calculate what D2 would be, the corresponding density. The mass will be the same. The mass of the helium stays the same. So how do we figure out the volume? Well, we got to derive an equation that'll work. So you start by going PV equals nRT. Circle everything that stays constant. Pressure stays constant. They tell us right here. Assuming that the helium is ideal. Wait, where does it say it? Oh, right here. But the pressure is kept constant. So pressure is constant. Volume is not constant. Moles is constant because it's a sealed balloon. It's a sealed quantity of gas. R is always constant, and then temperature is not constant. Okay, so everything circled goes to one side, everything not circled to the other, algebraically. So you're going to get V over T equals NR over P. NR and P, all of this is constant. So what does that tell us about V over T? It must be constant. So then what we can say is we can say V1 over T1 equals V2 over T2, because that ratio stays constant. So now we can solve for V2. So V2 is going to be V1 T2 over T1. So you plug the numbers in. I'm going to let you do that, and you get 1.366 cubic meters. So the volume got bigger. as we expected. Okay, so this is 1.366 cubic meter. So now we can find density. Density is mass over volume. So take the mass, plug it in, take the volume, plug it in, and you get an answer of 0.13 kilograms per cubic meter, which is the answer to the question. Okay. Now, final thought. Could you have chosen a different volume? So this volume of 1 cubic meter, I just chose that. I just said, let's be easy, right? Could you have chosen a different volume? Yeah, but then it would have been trickier because, you know, for example, just hypothetically, what if I had chosen a volume of 0.5? Then would the mass have been 0.179? It would have been half of 0.179, right? So for problems like this, just go make it easy and just say, okay, make the volume 1 cubic meter. Okay.